Okay, so here's the question, and this is the question that you saw in the tutorial, right? So we have a CSTR, and we are given the flow rate of component A, and we are also fed with component B, and we have the reaction given to us as well. And you can see these are not in stoichiometric proportion or anything. You've got excess B fed here. And it doesn't say anything about C and D, so we assume there's none of that. So that's the reaction. And then we are given all the thermal properties that we need. So we are given the heat of formation. It should actually mention the formation temperature, but I can't see it right now. But anyway, we've got the heat of formation, and we've got the heat capacity. And those are two things you always want to look for at the outset, right? If you've defined your species in the system, we can see we only have these 4 species to think about. Then you want to check quickly, do I have the heats of formation at some reference temperature? Do I have the heat capacities? With that, you can feel confident that you've got all the required parameters to do your energy balance on a problem like that. So what's the standard heat of reaction? That's one of the things, of course, we'll need. And then there's delta Cp for the reaction. So that's defined very much in the same way that we define the standard heat of reaction. We define the kind of standard heat capacity of reaction, if you like. And then the question, is it endothermic or exothermic? So that's something we can work out. Should we apply heating or cooling to get a better outcome? And by better outcome, I guess that's deliberately ambiguous, because number one, you could talk about a better reaction rate. And to get a better reaction rate, you always want to apply heating. So to get a higher reaction rate, as long as you raise the temperature, the reaction rate will go up. But in some reactions, if you have a reversible reaction, or if you have competing reactions, undesirable competing reactions, then all those rates will also go up. So in the case of a reverse reaction, then the rate at which the forward reaction, the forward reaction rate will increase, but the reverse reaction rate will also increase. So it's a question, which one will increase more? And that actually then is related to whether it's endothermic or exothermic, or what's the better outcome. So sometimes you might increase your undesired reaction rates. So all of those things are what we have to consider as we go. Let's see. So the question that we have to solve, given this basic information, right? All this is very basic. This is the basic thermodynamic properties and so on. So we want to design a reactor, perfectly mixed flow reactor, so CSTR, a continuous stirred tank reactor. So we want to design the reactor that gets us to 80% conversion at steady state. And it mentions the system in question too, but I guess all the details are given here anyway. So it's saying that we can heat to 400 Kelvin. Well, not heat to 400 Kelvin. Your heating fluid is available at 400 Kelvin. And at what temperature will the stream exit the reactor? And we are given that we are entering at 400 Kelvin. Okay, so as always, best to make a little sketch here. So we've got our CSTR, and we've got component A and B entering, and it's going to react. We are going to get to 80% conversion. And so we will have A and B left over. So exiting will be A and B and C and D. And we seem to be either heating up or cooling down this reactor also. So let's see, does it say what type of heat exchange? Doesn't really say. So let's just assume it's a jacketed CSTR. So So it's jacketed. And our jacket fluid is available at 400 Kelvin, 400 Kelvin, but you'll say I'm pretentious. 400 Kelvin. And also for our stream here, T in is also 400. Let's just see, heating fluid, we know T in. No, this refers to the heating fluid itself. 300. So our feed of our reactants, that's 300 Kelvin. Right. So we want to know what the exit temperature is from this reactor. So that's the first question, right? So here, at what temperature will the stream exit the reactor? So let's just appreciate the problem. Yeah, we are feeding this mixture in. Excuse me. We are given the molar flow rates as well. And then we have a heat exchanger around this reactor. So it's going to react. We know that in the process of the reaction, the temperature will change. We know that we are not adding heat. It's not a, well, we are heat exchanging here, but the reaction itself doesn't generate energy. There's no such thing as creating or destroying energy, but it is translating energy from one form to another. So if you like, A and B are in a certain energy configuration. To keep those molecules stable as they are, there's a certain amount of energy in the stream coming in. And then to convert to C and D, we'll break bonds and remake bonds. So there's a certain other energy form. So per mole of fluid, there's a certain other energy that applies here. So the reaction itself is going to switch energy. So from the chemical, there's a kind of chemical potential energy and part of that will convert to thermal energy. So the reaction itself is going to change the thermal energy. It is going to change the temperature of the reactor. So even if we didn't have this jacket with the 400 Kelvin coming in, even without that, the temperature wouldn't change, just because the reaction will change it will change you from chemical potential energy to thermal energy. So the reaction is changing the temperature. And then we also have heat exchange due to this jacket. So that's also going to change our temperature. So as a result of all those changes, we want to know what's the exiting temperature. And in fact, it's more important than that. It's not about the temperature of the exit, because that is not, we don't really care about that. We can always add a cooler or whatever it is to drop the temperature or raise the temperature. We don't care about an exit temperature normally. But in a CSTR, the exit temperature is going to be the same as the temperature in the reactor, right? So T in the exit stream is going to be the same as T inside the reactor. And that might be useful to know because, for example, we want to know what the reaction rate is in the reactor. And the interesting thing about our balance here, right? If you look at our balance, this is what we derived last time, right? So this balance we had developed from an energy balance across the reactor. Now, this balance doesn't say anything about the reaction rate, right? Fine, it has a heat of reaction here, but even that, you don't need the reaction rate for this. You've got heat capacities here. Again, you don't need a reaction rate here. So in this, there's nothing about a reaction rate. This is just the relationship between conversion and temperature, right? Those are the two main variables. Whenever you look at this equation, the temperature and conversion, those are the two main things that we are interested in. Everything else we tend to leave constant. By the way, there's another temperature here. So these temperatures and the conversion, that's what we are interested in. So there's no reaction rate here. And we are trying to design this reactor. So when I read this problem again in preparation for today, I noticed I didn't actually ask for the reactor volume. So it's actually the case that you can answer this problem without calculating the reaction rate. But I did want to calculate the reaction rate. So I am asking here, in addition to what's in the tutorial page, I'm asking here, what's the volume that we need for this reactor? So to get to that 80%, what's the volume that we need? And then also added, how would this look for the PFR? Okay, so that's the question. Any questions about the question first? Okay, now let's develop our solution. So first off, I just made I just copied the equation. So that's the same equation given to us in the problem. And then you've got T's in two terms here. So here I'm just grouping T out. So T is in here. So this part UA over FA in. So that's there. There is another term UATA over FA in. So that's over there. And then here there's another T, theta CPIT. So theta CPIT, and then you do still have theta CPIT in over there. Right, so we've grouped out to T here and then divided by heat of reaction there. And then we can just solve this for T. So you can just make T the subject of the formula, and then it will look like this equation down here. So basically we want to solve this equation, right? And then when we check the problem, you can see that the okay, let's go from left to right. So X, the conversion is given. We are told it's 80% in the problem. We can see the first part does ask us to calculate the heat of reaction. So we can see we are going to have to calculate this. That's fine. And then, so that's one variable. And then U and A, if you look at the problem, we are given U and A, and just be careful that this is the heat exchange area. It's not the area, like the cross-sectional area of the reactor or the inside area of the reactor wall or anything like that. This is the heat transfer area, and that's the heat transfer coefficient between the reactor and the heat exchanger. So U and A are given. Then FA in, we are told, we are fed with 10 moles per second of A. So that's our FA in, where are we? So FA in, and then theta I, remember that's the inlet molar flow ratio. So, so theta B, and by the way, when you read this, always remember this is of the inlet. And at the inlet, we only have A and B. We don't have C and D. We aren't feeding products in. Obviously, we don't feed products in, but there's also no recycle, and that's how products may get in, but we don't have recycle here. So we just have A and B in. So theta A, remember we defined theta as the inlet molar flow ratio. So theta, capital theta, A or theta I is equal to F I in divided by our reference component. So we let A be the reference component. So divided by FA in. Right, so clearly then theta A equals, and then FA in over FA in is 1, and theta B is FB in over FA in. And in this problem, we are given that we are feeding 40 moles per second of B and 10 moles per second of A. So 40 over 10 is 4. So that's our theta B. We can write theta C equals FC in over FA in. And we've said FC in is 0. So this is a 0. And also theta D is then, for the same reason, that's also a 0. Right, so all our thetas are defined. What's the equation? This one, right? So all those are defined. Your heat capacities are all given. Your inlet temperature is also given. So here, all your heat capacities are given, and your inlet temperature is 300 Kelvin. Right, so all that is defined. Just double check here. Yeah, this T, all this is given. This TA is 400. That's the temperature of the heat transfer fluid, and FAN is given. So all this is known. Just heat of reaction we have to calculate. UA over FAN, that's known, theta. So the denominator is all defined. So we just need the heat of reaction to work this thing out. And to work out the heat of reaction, we say the heat of reaction, heat of reaction is going to be the enthalpy of products minus enthalpy of reactants. So we can say here H, and let's see, a good way to do that, don't you think, would be nu I times HI. Right, so this is the and there's a minus sign. We know last time we saw when we defined heat of reaction, we defined it with a minus sign like that. So this would be the so it's the heat of reactants, heat of products minus heat of reactants. And of course, this is by multiplying by the stoichiometric coefficient here, the signed stoichiometric coefficient, then that gives us, in effect, the net heat change due to reaction. Now, we have to be a little bit careful with this, because you see, your choice of base does matter. So if you ask for the heat of reaction, right, remember it's going to have units of joules per second, but it's per mole of species reacted. So this is joules per second, and it's also per mole of something. Right, so this is going to be the amount of energy that, the amount of thermal energy released to the reactor per mole reacted. And now we have to be careful about which mole reacted, because for every 1 mole of A that reacts, 2 moles of B react. So if we did this as energy per mole of A, so then we will get a different result to if we said energy reacted per mole of B reacted. So this heat of reaction is dependent on your choice of component. And the way I like to emphasize that is with a little dash and the component symbol. So this is obviously not strictly speaking the way you write units, but it may help you avoid many errors. Errors I see people making again and again, even at the postgrad level. So to avoid the error of multiplying by the wrong thing, whenever you write these heats of reaction, you specify your basis component. And in fact, what we wrote here is missing that. When we choose A to be our reference component, when we are saying this is the heat of reaction per mole of A reacting, then we have to divide here by the moles of, by the stoichiometric coefficient of A. What did I mean? To have gone. Okay, so that explains this minus sign here, right? If we are basing it on a reactant, then you want this to be positive for products. So if you have a product here, if nu A is C or D, then this is going to be, for C, it's going to be +2, and for D, it's also +2. So it's a 2 there, and then A is a -1. So new A is -1. So this is 2 over -1. So this is overall a +2. So it's +2 for C and D, and then it becomes a minus, right? If this is new A, so it's -1 HA. So it's products minus reactants. Okay. So that's the amount of energy the amount of thermal energy that arises for every 1 mole of A that reacts. Okay. So be very careful with this. I know the tendency is to say, oh, heat of reaction, it's kind of like a constant in there, so I'm just going to stick a number in. Just think carefully, what is the basis of the heat of reaction? Is it given per B or per C, per D, or what is it? And then get it to the right form, and and prepare it carefully this way. Okay, so that's our heat of reaction. Now we still need the enthalpy. So to calculate this correctly, we need to specify for each component that's equal to the heat of formation of that component plus, and strictly speaking, it's the integral of your heat capacity with respect to temperature. So that's how you calculate your enthalpy for each component. And if your heat capacity is approximately constant, then we can say this is approximately equal to this stuff. It's approximately equal to Cp delta T, where the delta T is your temperature of interest minus the reference temperature, where the reference temperature is the temperature of the reference point, the temperature of the formation. So we could say here HIF is the enthalpy of component I, where T equals T ref. Okay, so that's how you can get the heat of reaction. You start here. You are given the formation enthalpy. So HF is given, and then you use HF, and you take the temperature at which the heat of formation is given, and you take the temperature of interest. And at the moment, we don't know the temperature. This is a variable to us. So this is an unknown temperature that we are trying to solve for. So that's the temperature there. And then this should say CPI. And so that's how we get our enthalpy as a function of temperature. So if we stick all those in here, I forgot my summation symbol. Right, then that's so that's the heat of reaction as a function of temperature. So that's what we have to do here. We have to compose a function of temperature, and you stick that in there, and then you add them all together using those stoichiometric ratios, and that will define for you the enthalpy as a function of temperature. Your reference temperature, I just want to check here if we really don't have it. 10 P. Yeah, unfortunately, it doesn't look like I've set the reference temperature here, but that is information that's needed. So at a temperature, so let's assume a value of 300. You can actually look it up. It does say this is a continuation of the other problem. So if you just look in the other problem, we'll get the correct reference temperature. But anyway, just work with this value. And so you do this calculation. Calculate the enthalpy, stick the enthalpies in here, and then you'll get the heat of reaction. And the same approach applies for the heat capacity of reaction, right? So CP of the reaction is this kind of sum for CPI, right? And that's on a basis of A, and of course CP needs to be so this is per Kelvin. So CP delta T gives you your enthalpy. Okay, so that's that defines. Let's see. Did we need delta CP? Well, we needed it for. Yeah, we didn't really need it here. Okay, that's fine. But I think the second question asked for it or something. But anyway, we can get our heat of reaction this way. And then that was the only thing that was left over. So if you check your equation, this is what we are solving. The only unknown was here. So this was what we actually have is the heat of reaction at a given temperature T. Well, this one says at T ref. So this is a common approximation that you'll see. I think we talked about it in the last session, that if your heat of formation is high, right? So if you look back at this, so if your heat of formation is high in comparison with your heat capacity and your temperature difference, if this is high in comparison with this term, then you can say the heat of reaction is approximately just the heat of formation, just the term you get from the heat of formation. So if you make the approximation that this is negligibly small compared with this, then it's easy enough to get the heat of reaction. And I believe that's why the reference temperature wasn't given here, because we were going to ignore this anyway. Okay, so we will get the heat of reaction as a fixed number here. If it's a function of temperature, then that's a third occurrence of temperature, and then it's a little bit more work, but it's not much more. You then have to substitute in that denominator for all this. It's still linear in T, so you can still group this out for temperature and get an expression over here. Okay, so that's for part A. So this part A is just to give you a bit of practice working with enthalpies and temperatures. I know you've done all that in your thermodynamics course, but it is good to have a refresher and be able to do that in this course. We do use the energy balance quite a lot. Okay, any questions or comments there? Right, so that's how you do the first part, and then yeah, delta CP in the second part we just showed. You can use that same approach. Leanda. Okay, guess that wasn't a question. Okay, so that's that's how we answer these two parts. And then the question, is this endothermic or exothermic? So if it's negative, right? If it's if delta HR is negative, then that means your heat of your well, first off, if it's negative, then it's exothermic, right? And let's think about that. If it's negative, if delta HR is negative, then that means that the enthalpy of your reactants is greater than the enthalpy of your products, right? And that means that after reaction, let's say everything reacted, right? All of A and B converted to C and D. And we are saying that the that enthalpy, heat of reaction being negative, we know that must mean the chemical energy, the enthalpy of the reactants must be greater than the chemical energy of the products. So you had more chemical potential energy in A and B, and now you've got less chemical potential energy. that means you must have more thermal energy. That means you've converted chemical potential energy to thermal energy. So exothermic is delta HR is negative. It means you've got less chemical potential energy, means you've got more thermal energy. That means your temperature has gone up, right? I don't know which one it is. I didn't work this out here. I'd have to check my notes somewhere. But work it out and see if it's negative, then you know it's exothermic. It means the temperature is going to go up. If it's endothermic, then let's just talk through it again for practice. So if it's endothermic, then delta HR is positive. So delta HR being positive means that the enthalpy of the products is higher than the enthalpy of the reactants. So enthalpy of products being higher means now you've got a greater chemical potential energy. So there's more energy that goes into making the bonds and now the molecules, just the fact that you have C and D, there's more energy in the molecules C and D. So that means the original energy that you had has all that has been depleted, in addition to which you got energy from somewhere else to make C and D, and that somewhere else is the environment. It's the temperature in the reactor. So you must have taken in thermal energy to make C and D, because A and B by themselves, they had less energy than C and D. So endothermic means your reactants have a higher chemical potential energy, means you must have stolen energy from the temperature side of things, from the thermal profile of the reactor. So endothermic means your reactor temperature goes down. Okay, any questions or comments on that? Right, so that's endothermic and exothermic. So that's it. And now, well, I think we've just done this, right? So we want, so what temperature will the stream exit at, right? So that's, so we've just, we said that's the equation, so we can just solve for T now. So we've done part C. Okay, now part D, what's the required reactor volume? So I've just, again, for those who joined a bit later, I've just added parts D and E because as it stands, you can answer this question purely from the energy balance. And if you go back and look, right, you might not believe me when I'm telling you this now, but if you go and look back at the notes, to derive this equation, we didn't use a reactor at all. Everything we said there was purely written in terms of conversion of reactants and products, and everything was in terms of enthalpy of before and enthalpy after. We said nothing about the nature of the mixing or about the reactor or anything like that. So this equation is true whatever your situation is, whatever type of flow you have in your system. So this is generally true, and it's important to note then this equation applies in all reactors. Okay, whereas our design equations, those apply for our specific reactors. I'm just looking for my, yeah. So there's your CSTR balance. So now we know it's a CSTR, and the same balance does apply. Let's just think about our CSTR balance. So there's our balance. Maybe let's try and use the picture. So our CSTR, it's always perfectly mixed. So wherever you look in the CSTR, you will have the same temperature. Whatever point you choose there, you have the same temperature, you have the same concentration, the same conversion, the same reaction rate. So at all points in this reactor, you've got the same reaction rate. And so this balance, this is true. So for a CSTR where you've got perfect mixing, this is true, and also our energy balance is also true. It's not like we've that they are in conflict in any way. So we've got that reactor, and our reaction rate. If we want to solve this, we need to apply the reaction rate in here. Now, this reaction rate is going to have a specific dependence on temperature and on the concentrations, right? So the reaction rates is some kinetic rate constant, which we know is a strong function of temperature. And if it's an elementary reaction, then it's CaCb squared, right? So remember, elementary reaction, your reactant raised to its stoichiometric coefficient, the product of all those. So Ca times Cb squared, right? So that's our reaction rate. And this Ca and Cb, we can rewrite in terms of the conversion. Remember, we have that the molar flow rate of any component can be referenced to, or can be written in terms of our reference component A, if we use the inlet molar flow ratio and the stoichiometric coefficients. So this is the molar flow rate of any component I. We just take its inlet molar flow ratio and we take its stoichiometric coefficients and multiply by the conversion of A. And if we divide both sides by the volume, then we can say the concentration of any component I is equal to the concentration of component A times all this stuff. So our balance here, the reason I did all that was because we want to get rid of these concentrations. So Ca, we can always write as Ca in times Ca in times 1 minus XA. And then Cb squared, we can write as, right, there's the squared. We can write that as Ca in. And for theta b, we said that's a 4. And nu b over nu a is minus 2 over minus 1. So that's going to be 2 times XA, right? And so if you look at this, your Ca in, let's retrieve that from here and just Ca in squared times Ca in. Let me actually do this on a separate line here. So I'm going to retrieve the Ca in. So this is Ca in squared. So let's take that out here. So Ca in squared times Ca in is Ca in cubed. And then this is 4 minus XA squared. So we can just write it like that. Okay, so that's the right-hand side. And then on this side, we have this. And we do know the conversion, right? We are told in the question that the conversion is 80%. So you can just stick 80% in for all these XAs and work out these numbers. And then the molar flow of A in is known, 10 moles per second. We can calculate the temperature, right? We did that in part C. So we did the energy balance here and we calculated the temperature. So we do have temperature. So all we need is this little function K of E. So that's the Arrhenius expression. So the Arrhenius coefficient times E raised to the minus, this is E over RT. Right, so we need A and E. So if we just stick those numbers in, we've got the temperature. R is the universal gas constant, 8.314 for SI units. So we can calculate this K. Again, I just made this up. I just added this to the to your tutorial. So A and E are not given here, but if you look up where we first defined this problem, I think it's there somewhere along the way. So A and E, you stick those in there, that gives you a K. So you've got the K. CA in, let's see, well, if we are solving for the volume, then we need to keep that volume out there. We should rewrite this as F A naught cubed over V cubed. It's volumetric flow rate. There's too much data missing from here. This is Q. So yeah, you do need additional information to solve this problem. So yeah. So anyway, like I said, I just added that. Thought it would be nice to have a look at that, but I can see to really get numbers, we need to add more to this problem. Okay, any questions or comments on that? Okay, now the last one that we also just added. So again, we won't be able to solve this, but let's think about how we would solve this. So when I say here, develop for the CSTR, what we mean, of course, is what is the required volume to get to X equals 80%, right? So, so if we want to do this for the PFR, then, right, so let's just separate things a bit. For the PFR, right? So for the PFR, we have the design equation. So this is, of course, still true. So we have that, and then we've got our energy balance. So that's the other one. And again, we can substitute for the reaction rate. So we've just worked out the reaction rate. Let's see, should we use this form? Let's rather use this. So we know, strictly speaking, given it's an elementary reaction, this must be true. So we can substitute this here. Right, so that's one thing. And yeah, the rest does follow. So again, we can rewrite this in terms of FA naught. So that concentration, how did we get rid of this here? The concentration, so we wrote it, yeah, you had to write it in terms of CA naught. So you need the volumetric flow rate. So if you have the density of the inlet feed, you can convert this molar flow rate into a volumetric flow rate. So there are those small conversions to do those shorter calculations to just get a volumetric flow rate. Then you can convert between molar flow rates and concentrations and so on. But anyway, for this one, yeah, let's just write this as a CA naught, and this is going to be, as we said before, 1 minus XA and CB squared. So this is 4 minus 2X XA squared. Okay, so this is our equation for the PFR. Now we've got this T here. In the case of the CSTR, it was possible for us to say, well, we can just use the value that we worked out in part C, right? And it's not just because in this tutorial, in this case, all this is changing as a function of position, right? In this case, your temperature is a function of conversion. So we have to acknowledge this is a function here, because all this is going to change now. So, okay, let's just save this and save a new one. So today is 8/24. So that was, let's save another one. Okay, so now we have the PFR, right? So we've got a tube here. And now we have to acknowledge that the conversion is changing as we look down this tube. So component A and B will enter at a nice high concentration. And as time passes, well, as we progress down the tube, they will be converted, okay? So what that means is that your temperature is also going to change, right? Remember, our temperature, looking at it that way, temperature is a function of conversion, right? So maybe we should be pointing here. We can see temperature is going to change as your conversion changes. So as X changes, you have to use this equation to calculate your new temperatures. And let's say, for instance, that the temperature was actually rising. So say temperature was doing that. Then that means we need to recalculate our reaction rate each time. So we normally do have to recalculate it each time because conversion itself is changing. But now, in addition to conversion changing, we also have to incorporate this additional dependence on conversion. So you see, for the PFR, the integration just got slightly more complicated because K is changing as well now. So before, when we were doing isothermal design, we just said, oh, there's a K over there, by the way, and then we carried on with the rest. But now we can't say, by the way, for this K is a very strong function of temperature, and temperature itself is a function of conversion. So we have to respect this relationship, K, and at least we have this balance. So that's the great utility of this balance, right? Even in the non-isothermal case where where temperature is changing and so K is changing, we now have this additional relationship between T and X. So in our new developments where temperature arises as an unknown, at least we have a relationship with X. So wherever we see T, we can substitute for X. The other nice thing is when we derived this relationship, we didn't use anything about the reactor. And so this equation always holds. So we can always relate temperature to conversion like this. Okay, any questions or comments there? Okay, if we look now at some of the other questions, you can see that it's talking about equilibrium, it's talking about reversible reactions. So we need more development, more theoretical development. Maybe before we do that, we should just chat about the third possibility, the batch reactor. So let's just add this batch reactor. I'll just say it like that. Okay. So for the batch reactor, we know we have dx dt equals f a naught. Well, it's na naught, and what's this v? Well, the way I really think about the batch reactor is it's dCA dt equals RA minus RA, right? That's your batch reactor. So you can rewrite this in terms of FA naught and X, or NA naught and X, and all of that. But that's our batch reactor. So again, we have the same situation. For RA, we are going to get this expression. And on this side, we can write this dCA here as CA naught, should say minus, and then XA. Right, so again, for the batch reactor, we could ask, how long does it take to reach a conversion of 80%? And we then have to acknowledge that the temperature will be changing during that reaction. So in our batch reactor, we start with a certain concentration, so Ca0 and Cb0, and there's some initial temperature in there. And then as the reaction proceeds, so for example, if it's exothermic, then the temperature will rise. And as the temperature rises, the reaction rate will also rise. And so that will show up here. So by virtue of the temperature rising, K will increase, but this part will decrease. So as the conversion rises, then the concentrations go down. So again, our balance becomes a bit more complicated because we have the temperature effect, and at least we still have the energy balance. So you would use the energy balance to update your temperature each time, and you would step forward. If you want to imagine the integration, right? If this is conversion and this is time, you can imagine, let's say we had some conversion at some time, then so we have the conversion at this instant in time. So we can substitute all these conversions here. We also substitute a conversion here that gives us a temperature. We use the Arrhenius expression that gives us a kinetic rate constant. So that defines this. Then, as we said, all this is defined. So all this gives us one number. So that's giving us a gradient. So we can take a small step forward, and let's say we get to here. So that defines a new conversion. So again, we can put in a new conversion here and here and here, and then we get a new temperature and a new K, and that gives us a new slope. And so we can step forward and span out our solution. Same approach applies when you are integrating along this tube. Okay. All right. So that's for the batch reactor also. Okay, now looking at the tutorial, I wonder, we must really take a break in between somewhere. Let's see. So maybe just to introduce this, and then we can look at the break. But for this question, we are asked a couple of different things. Now it's talking about an equilibrium line and a maximum rate path and all that. So we are not familiar with those terms, but never mind these specifics. If we just think about this problem, we have a reversible reaction. And that seems like, okay, that's not such a big step forward, but if it's reversible, then we have to rethink what's going to happen in our balance. We also have to think about our reaction energy and how that's going to change things, because we know if it was just a forward reaction, then then that reaction will change our energy. But now if it's reversible also, that's going to change our energy balance in some other way. So it looks like we need to be more careful. And there's also going to be some kind of equilibrium that we will achieve. So between A and B, we'll get to some steady state, even if it's in a CSTR. So now we can see there are some more complications, and we need to do our development a bit more carefully. So maybe maybe we need to take a break now. I'm not sure. Do you want to take a break or keep going? I'm good either way. Okay, default is we keep going. Yeah. So if you don't speak up now, we'll just keep going, no break. Okay, looks like no break. All right. Instead of trying to jump into the question, let's then introduce this notion of equilibrium. And that is in a new set of notes that I have uploaded. So we are now talking about non-isothermal reactor design. So we've done the energy balance in the previous session. Now we want to say, well, like we did before with the Levenspiel plot, right? We were navigating that plane. We had nature giving us the curve, and now we want to see, can we still design good reactors? Can we get the smallest size reactor and all of that? Can we still do all that even when the temperature is changing? So one of the first things we worry about then is that we generally, or not generally, we most often have equilibrium issues arising. So in most real world reaction systems, you've got competing reactions and your reactions may be reversible. And so a certain equilibrium can arise in our systems. So we know from thermodynamics that equilibrium relates somehow to enthalpy and energy and so on. Because remember, if you think about the Van't Hoff equation, if you think about the Gibbs free energy and the relationship with equilibrium, it's all related somehow. So let's just develop things carefully and see how we go. So so number one, we suspect now that there will be some equilibrium dependence on temperature. So if we think about, again, our reactor, so let's so if you think about in, let's say, a little batch reactor, that we have even the most basic reaction like this, but it's reversible, right? So A and B reversibly reacting. And let's say we charge this reactor with pure A. Then if we were to draw the concentrations of A and B as a function of time, we can imagine A will go down like this over time and B will go up. So the concentrations will change in time like so. But obviously, these are two different types of species. And so they have different enthalpies. And so the temperature is also changing while this happens. And so the reaction rate, let's not worry about that. But A and B are reacting, and they don't settle down to zero. Neither one settles down to zero, right? As much as A forms B, B also returns A in the reverse reaction. So A generally won't go back to zero, won't go down to zero. And similarly, B is formed, but B returns to A. So B won't go to a pure one either. So they will reach some equilibrium where the forward reaction balances the reverse reaction rate. So the two rates will become equal. I should say here K1 and K2. And so it doesn't mean that the two rates become zero, right? The forward reaction rate, if you like, R1, which is A going to B, that doesn't become zero. So at this stage, and let's be explicit here with a 1. So 1 is somewhere up here, which is not a pure one there, right? So so as long as you've got some A in the reactor, the forward reaction will happen. And as long as you've got some B, then the reverse reaction will happen. So but there may come a time when those two reaction rates equalize. So let's do some small development around that. So we've got A and B reacting. So A, actually, how do you make that in this? Okay, I guess most people use this one. It's not quite correct, but anyway. So A and B reversibly reacting. And so we can define for ourselves R1, so the forward reaction rate, or maybe RF, right? Forward reaction rate equals, and that will be K forward reaction rate times CA. That's a forward reaction, and then you have a reverse reaction, R. That doesn't look good. KR, and that's CB. Okay, and then you can say at equilibrium. Well, let's before we say that, let's say also there exists a net rate of reaction. R net equals R F minus R. Okay. So at equilibrium, R net equals 0. And so when R net equals 0, RF equals RR. So KF times CA equals KR times CB. Now, we also know that we can rewrite our species in terms of the reference conversion of A. So we can write this as a CA naught times 1 minus XA, and CB we can rewrite as CA naught times theta B minus, and we can say nu B over nu A. We can see nu B is a plus 1 and nu B is a minus 1. So nu B over nu A is going to be minus 1. So this is going to end up as a plus XA. Right, so that's the concentration of B. And so that's A and B. And then we can see here that the CA naughts can cancel as well. Same thing on both sides. And what we'd like to do is acknowledge that KF is a function of temperature and KR is also a function of temperature. So that's all true. And now we can rewrite this as, well, we can rewrite this in the Arrhenius form. Well, okay, let's just not have so many lines here. So this Arrhenius, we can rewrite this as the pre-exponential factor, and we have to be specific that it's for the forward reaction. So AF, and then E raised to the power minus, and this is going to be EF over RT. So that's your rate constant for the forward reaction, and then for the reverse reaction, it will be the same thing, but with R's instead, right? So that's it. And then what we can do is divide both sides by this whole thing. So we can write here, let's see, which way do we do this? I think that's the way we do it in the notes, but anyway. So let's divide all this on both sides. So we will have here AF over AR, and then when we divide by exponential, so if we divide by this, then that's the same as subtracting this from that. So what we can do here is rewrite this as EF minus ER, like that. And then also we may as well take this, we can divide this out. Okay, And I think the way I did it in the notes is to say, well, if B is a product, let's assume that we don't have any B initially. So theta B is a 0. So if no B initially, then that's a 0 there. And one thing that we should have been more careful with is that this is a special condition, right? We know this is not generally true. This only happens here, right? The two reactions are only equal here. So here they are in equilibrium. Before this, they were not in equilibrium. So before that point, what I'm trying to say is this is a very special case. So there is only one specific set of concentrations or one ratio where this happens. It's going to be such a mission now. I'm going to have to. So that's the special X. That will help speed things up. Right, so all this happens at a very special conversion. There's only one conversion where all this applies. Okay. So what this shows us is that there exists a relationship between the equilibrium value of conversion, XA star, and the temperature. Right, because if you look at this, you can see all these are constants. The pre-exponential factors for both reaction rates, those are constants by the end of the day. This is a constant, your activation energy, and this is the gas constant, right? The universal gas constant. So everything is a constant except for T. So on the left-hand side is only a function of T. On the right-hand side is only a function of X. So by the end of the day, we can say there exists some relationship that looks like this. Okay, and in fact, you can multiply this out and solve it, and you can show it's done in the notes. Let's see here. So we've talked through all this stuff. Yeah, here. Here also we've introduced this so-called the equilibrium kinetic constant. So you can define that, you can say, let the equilibrium constant equal the ratio of the kinetic rate constants. I must say, whenever I show this, I always feel like you've already seen all this, that this is basic chemistry, even at the high school level. I mean, things have changed a lot. When I was in high school, we covered a lot of this stuff already. But even without that, this is third year now, you've seen all this in your chemistry classes, right? So hopefully this is already looking familiar to you. Okay, and here, of course, this constant is not so constant because it depends on temperature. So you can define the equilibrium constant, and so that's the left-hand side here. Okay, equilibrium as a function of T. So the nice thing with this is it tells you that the equilibrium conversion as long as you have the temperature. So if I tell you the temperature in the reactor is 500 Kelvin today, you can go and stick in that 500 Kelvin here and then stick it in there, and then you can calculate an X. You can come back and tell me, well, then that must mean at equilibrium, it's 30%. The conversion is 30%. So I would like to ask you then, is this a good value? Do you like this value or you don't like this? I don't mean, is this in terms of your reactor? Is this a desirable conversion for you? Any takers? Maybe thumbs up if this is a conversion you would like to see in your reactor. And then thumbs down. Do we have thumbs down? Or I don't know if there's a crying face or something. Yeah, use a non-thumbs up, anything, if you don't think this is a good conversion to have in the reactor. Let's see, some reaction. Is one person going to give me a reaction? Sure, I'm dying at you. Thumbs up if you want XA star in your reactor. Any reaction other than thumbs up if you don't want XA star in your reactor. Yeah. I wonder if anybody is actually there. Okay. Okay, thanks. Somebody did react. Okay, so thumbs up. So let's think about that, right? Let's look at our batch reactor, for example. So now you can see here, we are in equilibrium, right? So by this stage, it settled down and we are in a stage of equilibrium. Now, is any net reaction happening here? Right, we've settled down. We've said the two rates equalize by the endpoint, and so we are at equilibrium here. Now you can see we are not converting any of A anymore on balance, right? A is staying at some concentration, or what is this? I guess the blue line was B. So yeah, you've reached the steady point where on balance, you are not producing anything. You just maintain a steady amount. And similarly, in your CSTR, if you are operating at equilibrium, right? If your reactor is big enough, then it means you've achieved some conversion. So for smaller volumes, you had some other conversions, and then you've reached somewhere. So you are at equilibrium. You are not on balance producing. There's no chance to improve on A anymore. That means on balance, you are not producing more A than you were before. So this is actually a point to avoid. You don't want equilibrium, right? At equilibrium, your net rate is 0. You don't want a net rate of 0. You want to be converting as much A as possible to B. It doesn't mean the reaction is not happening, but your reverse reaction is competing at the same rate as your forward reaction. Maybe that's the best place to look at it. You want a low return rate. You want A to go to B. B is more valuable to you, more profitable. So you want more A going to B. You don't want to be in a situation where as much of every time you form B, you form the same amount of A again. So you don't like this. You don't want equilibrium. So all this development is for us to identify a region to avoid. So equilibrium is the place that we want to avoid in our reactor. And what we have now is a nice way to get the equilibrium value as a function of temperature. That's what this equilibrium does for us. And for your tutorial, I hope this question is asked. Yeah, this kind of goes straight into very specific things, but I would like to add here, draw the equilibrium line as a function of, well, draw the equilibrium line means x equals x of t, and we should say x star. And in fact, maybe we should do that here quickly. Let's see. Let's take this example and just okay. I should actually do this in our folder, in our Dropbox folder. Just a second. So, let's see. So here we let's create a new notebook, and let's just save this as isothermal design. Okay. And what we want to do is set a lens space. So we're going to need to import and then here we can say t equals lens space 300 to maybe 800 using 50 points. I'm supposed to say numpy lens space, right? Space, okay. And now we want to let's in fact work out a couple of rates and things. Can we do that? So let's look at conversion. So let's say A forward equals, I'm just going to put in some arb values. And of course, our gas constant 8.314. Okay. Let's see, let's work here. So, oops. So this is KR. Okay, so you agree that's our two constants. And what are we wanting to do? Let's see. So let's look at how let's simply plot some rates to begin with. So we can say R forward equals KF times, and then let's see what's going to change here. I don't want to put the energy balance in yet. Let's see. Well, let's just work out the equilibrium constant. So equilibrium constant is KF over KR. So let's plot that. So Do that. Just a second. That's the pie plot here, right? Matplotlib pie plot. Okay, and then we just want to do here plt.plot. We want to plot. We can just look at how the equilibrium. So equilibrium is rising here. In fact, let's make it painfully obvious which way it's supposed to go. So if we change ER to 30,000, now the reverse reaction is higher than the forward reaction. I guess here, if your E's are equal, then when you subtract those two, you'll get a 0 x above 0 for, so KE won't be a function of temperature anymore. But it is, okay, that's fine. So maybe let's keep these the same and make this one, make the reverse rate higher. So now you can see, right, clearly the reverse rate constant is going to be higher than the forward rate constant. So as temperature rises, your reverse rate goes, your reverse rate becomes higher than your forward rate. At least the constant goes higher. So your equilibrium constant goes down with temperature. So that's possible, right? Any values here are possible. Any positive numbers are possible here. So, so of course, if the reverse were true, if this went below, then it would rise, right? So here it's rising. So if your forward rate is greater than your equilibrium, your constant, your kinetic rate constant goes up like that. Okay, so that's one. Now, what we are really interested in is XE. So we've just seen in our development, X, let's see, where was it? It was on the PDF, right? Right, so XE has this relationship, right? We derived that the equilibrium constant is related to KF and KR, and then we can rewrite it in terms of KE. So we can say here, XE equals KE over 1 plus KE. So let's plot XE as a function of temperature. Okay, so here, looks like our ranges are not great. So let's extend this a bit. So let's go down to 200 here and go up to maybe 1,500. Okay, so you can see things are starting to curve. Let's drop it even further, going all the way down to 50 Kelvin here and all the way up to 2000. And so you can see it's a kind of S curve. So equilibrium looks like this. You can see also the equilibrium numbers between 0 and 40. And if you look at the equation, you can see that when K goes off to infinity, you get here infinity divided by infinity, right? 1 is small compared with infinity. So infinity, so this thing tends to a 1 when K goes off to infinity. When K is a 0, it's 0 over 1, and so that's a 0. So the lower limit is a 0, and the upper limit is a 1. So those are the limits for X equilibrium. In this one, it seems, yeah, we are not going that, yeah, you can see it's kind of tapering off here. So clearly at the higher temperatures, these two, yeah, they don't increase much faster than the other. So it settles down to some value there. Okay, so that's how we can get the equilibrium values for our reaction. And this then defines for us the region to avoid. We said we don't like equilibrium because that's where the net effect is zero. We aren't producing on balance more of our product. So what we want to do is avoid this region. And when we say avoid the region, we are talking as if we have a choice about where we sit in the space. So let's think about that. Do we have a choice about where we sit? Where's my little scratch pad? So save that. So I'm just going to copy this picture. It's not a great one. Maybe let's up the resolution and try that. Too much. Okay, let's just use that. So we have this equilibrium curve, and we are talking as if we have some choice about where we sit. So let's think about our real reactor, or let's imagine a batch reactor here. Now we are free to load whatever we want into this reactor. We could put A and B in. We could put in some mixture of A and B. And so we can pick what conversion we are going to start with, right? So if we load, for example, you know, like if we've defined the conversion, let's think about this. If we pick a mole fraction of A and mole fraction of B, such that it's equivalent to a certain conversion. So let's say we start out with pure A. So XA is 1 initially. So let's say let's call this scenario 1, okay? So XA is 1, and then we watch how this goes, and it goes through that. And so we say, okay, when XA, so it started out as a 1, and then it reached maybe 0.4 over here. So we can look up and say, okay, what was the mole fraction of A at this point, right? Well, it's 1-to-1, A and B 1-to-1, so this is 0.4. So if we load enough B so that we start at 0.4, for example. So if we put A and B in here, and if we put in a mole fraction of 0.4 for A and 0.6 for B, then that decides already what conversion we've started with. So we are in fact free then to choose any value here to start with. So we can, just by controlling the mole fraction of A and B, we can pick any value there. And then also we can apply heating and cooling. So let's say we have a heating coil, and let's say we also have a cooling jacket. So you can control the temperature in this reactor. So you can also choose any temperature here. So let's say we chose a temperature and a mole fraction such that we were sitting here. Then you would actually find that the tendency by the system is to move towards equilibrium. You will find that if you leave this reactor under those conditions, right? If you started off with that at that point, right? You've just chosen a temperature, you just heated it up to this, what is it, 1,800, let's say. So you heat it up to 1,800 and you stick in 0.05 mole fraction of A. So you forced the system onto this point. What you will find is, right, remember there's the thing about nature always goes to equilibrium. And there's also Le Chatelier's principle that we've all heard about in high school. So in those, according to those two, our system is always moving towards a state of rest. And our state of rest is this equilibrium, right? The name even tells you that's, so our system will tend to do this. The reaction rate or the reaction will happen such that the conversion will go up, right? So conversion goes up in this direction, and the temperature will tend to go down. Temperature goes down in this direction. So that's what's going to happen. Your conversion will rise and your temperature will drop until it reaches, well, it will never really reach, the driving force will go down, 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 and you never reach there, but that's what the system will tend to do. So it sounds a bit like I'm asking you to be intuitive here, because you could say, well, then how do you know you are going to that point on the equilibrium line? Why didn't you go this way? Or why didn't you go this way? And the answer is, well, we are already constrained about how we are going to go there. We are going to move towards the equilibrium line, but specifically how we go there is already determined. What already determines that? I've become kind of afraid of asking questions in this class now. Does anyone want to hazard how? Why do I claim we are already prescribed it? It's already fixed how we are going to go to equilibrium. Oh, these awkward silences. You know, even my second year class is talks more to me during these sessions. Well, look at what we are asking about here. We've said is conversion, and this is temperature. And don't we already have this? X of T. We already have defined this relationship, right? Our energy balance. So in that first tutorial problem that we did, we were using this no problem, right? The whole solution approach was based on that there exists a relationship between conversion and temperature. So it looks like we just have to use that. We can pick any starting point, as we said, and then we just use our energy balance. And you will find that the energy balance will always point towards equilibrium like this. And we can start to see a bit of that if we just look at the equation. So let's take a simpler version, right? This let's, for example, just say that it's not adiabatic. So, okay, the easiest way. Okay, we have this. Yeah, okay. Can't really edit this. So I'm just going to paste it on here. Let's see. Yeah. Okay, I'm just going to cut this out. So let's say we are not adding heat or removing heat from the system. So, so this is zeroed, right? Let's just say we took away our heat exchange. So there's no heat transfer area, so that zeroes out, right? So we are thinking now about the case where, for example, it's just a batch reactor and we are leaving everything to react. So we forced it onto this point, and the curve is sloping like this. And if it's an exothermic reaction, let's see here. There's a minus sign missing, by the way. There's a minus over here. Let's see, minus delta H. No, that's right. So this is actually an endothermic reaction, right? When the curve slopes like this, we'll prove that just now. But when the slope curves like this, right? I'm talking about the equilibrium curve. So when the slope curves like this, it's endothermic. If it's endothermic, then this is so the minus sign is here, right? So if this is endothermic, then we've said earlier this is positive, right? So this being positive, and then over here, if we look at this, this is all positive, right? The inlet flow ratio, that's just a ratio between 0 and 1, so that's positive. Heat capacity can't be negative. And let's just say T is more than T in. So your, well, yeah, sorry, I'm going a bit back and forth here. The right way to do this is as a dx dt. So let's just do this properly here. And I want to just check back at what we had for our energy balance. So I just want to check the notes for the right sign. So let's do this more carefully. Okay, so that's what we have, okay? So let's accept that this is correct. And then if you look at this, you can work out the gradient dx dt. So if you were to write this out, so dx dt, dx dt equals, so if you look at this, dx dt is going to be this stuff here. So it's some beta I, some beta I, C, I, and all of this is divided by delta H R, and there's a minus in front. It's written in this, seems to be written there. Okay, okay. So that's there. Yeah, so if you look at this, if we say that the that delta HR is endothermic, so not so if it's endothermic, the endothermic implies that delta HR is positive, and you can see the numerator, all this stuff, this has to be positive, right? Beta, CPI, we just said all that is positive. So overall, this is going to be negative. The denominator is positive. So overall, this is negative. So delta HR is positive. That gives us that dx dt, dx dt is negative. And you can show by the same token that when delta HR is negative, then dx dt is positive. You can also show, and we do still need to prove that when it's endothermic, that the slope, that the equilibrium line is going to slope like this. Let's just draw this again. So in your XT line, if it's endothermic, then it's going to look like this. Right, so that's your equilibrium line. And then we've said if it's endothermic, so all this is endothermic, right? So endothermic means it's sloping like that. So if it's endothermic, then dx dt for the operating line, right? So what does that mean? Let's just say energy balance, right? So our energy balance line, the slope of it is negative for x and t. dx dt is negative. That means our energy balance line is doing this. So that's telling us that as long as the line slopes that way, it looks like this. And by the way, that's for endo. If it's exo, so for exo, the line looks like this instead. So xt plot will have to look like this. And we've said if it's exothermic, exothermic. So if it's exothermic, then dx dt is positive. So in the case of the exothermic line, it's pointing like this. So you can see it's always pointing at equilibrium. Our system is also always trying to run away to equilibrium. Now, in terms of proving about which way the line is going to slope, we can use, where are you? We can use our, equilibrium slope. So, we said earlier, XA star equals K, should say star, but anyway, KE and 1 plus KE. So this is what we have. And well, you know what, let's do it using let's do it using this. So let's look at if we have, well, in fact, we already showed it. So if EF is more than ER, right, your activation energy for the forward reaction, if that's more than ER, then that is endothermic, right? So if you run that, that's what you get. If ER is more than EF, then it slopes the other way, okay? And we'll see just now through the Van 't Hoff equation, the relationship between the heat of reaction and the activation energies. But at least from this, we can see experimentally, at least, that still fits what we've been saying there. Let's actually look at the thermodynamics to prove this is true. So yeah, here we go. The Van 't Hoff equation gives us this relationship, right? So if you look at your Gibbs free energy and the relationship with the heat of reaction, you eventually show, according to the Van 't Hoff equation, this is how the kinetic, the equilibrium constant relates to the temperature, right, through the heat of reaction. And your, let's see, yeah, here it comes. So what you can do is expand on the heat of reaction term. We know we can rewrite that as a formation heat, just slightly different notation here. That's formation heat, and that's the heat capacity part. And then this is written in terms of derivative in temperature. So if you integrate this, noting that you've got a 1 over T squared here, then that will integrate to a minus 1 over T, like shown here. And then that's basically out there. And you do have this extra term for, yeah, there's a T squared and a T there. So just work through that and you'll see you get that integral. Okay, so that's the integrated form. Then you note that, of course, you arrived at this heat of this net reaction from these two kinetic constants. So you park this result for now, and you say, well, I can get my relationship between equilibrium constants if I just look at my original kinetic rate constants here. And we know Ke equals K1 over K2, K forward over K reverse. So if you do that, right, we showed this earlier. So if you compare these two, right, if you take Ke at one temperature divided by Ke at another temperature, you can see there's where the temperature dependence arises. And if you compare these two, I can see I didn't do it properly here, but if you just do that, just compare that 1 over T there with that there, you'll see that the two equations look the same, right? You can regard this as Ke at 0. So when you compare these two equations, you can see here that delta HR is related to the activation energies this way. So delta HR is actually equal to activation energy of forward minus activation energy of the reverse. So that's extremely useful. It means we can calculate the heat of reaction even without the enthalpies of the components, as long as we know the activation energies for the two reactions. And so that's what we also saw in our Python notebook. When we set E1 higher than E2, when E for the forward reaction was higher than for the reverse, we got an endothermic reaction, right? Delta HR positive, and we showed the reverse. So I know I'm waving my hand a bit too much through this. I didn't make a good set of notes on this, but if you work through it yourself, you can show that when you compare those two equations, you get that. Okay, so we can prove for endothermic reactions, it looks like this. It slopes this way, and then our energy balance points that way. And for exothermic reactions, it slopes this way, and so the energy balance points that way. So in a way, we've proved the case, right? We've proved what we saw in Le Chatelier's principle, things that we just heard that sounded like they were real. You can prove that that's true. Okay, any questions or comments there? Okay, so you can use all that then to answer the questions in that tutorial, or the first parts of those questions. And then we are going to use that in the session afterwards to actually navigate the XT plane. Okay, so there's the tutorial. And in here, it's asking us to draw the maximum rate path and the equilibrium. So you can define at least the equilibrium line, and then think about what other rate lines we could draw. The equilibrium line is where the net rate equals 0. Can you also draw lines where the net rate is not 0? Okay. Show the operating line of the CSTR. So in other words, draw the energy balance and see if it points at the equilibrium line. So don't worry about maximum rate path yet. Just do that part and draw the operating line for the PFR, also looking at in which direction it's pointing. And yeah, that's enough for right now. So do that part, and then we'll talk next about navigating that plane. Okay, any questions or comments there? He said in vain. Okay. So if not, we'll call it there for today. So thank you all for coming. See you in the next one.